So welcome everyone to this lesson. I welcome everyone to this lesson. I remain your Normally your teacher is supposed to be Mr. Kelvin, but today I'm Ikechukwu and I'll be your tutor for today. The topic for today's lesson is types of chemical reaction, and as usual, our normal 9 till 10:30. I don't know if, as usual, too. If you can't hear me at any point, or probably you're not seeing my screen, just turn on your mic and say something. I will not be seeing your chat inputs. So in case you have anything you want to tell me or ask me, turn on your mic and say so, please. Because as I'm on this screen, I would not be seeing anyone. So thank you. Before I start, can everybody hear me?
Yes, you can.
Okay. So let's go into the lessons for today. Before I go on, let me first ask, does anyone have questions from the previous lesson? Any question at all from the previous lesson? So that we could treat it before going into today's lesson. Probably during your because of your study, personal study, you had some confusion or stuff like that. Is there anyone with any confusion from the previous lesson? Okay, I would assume there is none. So I will start this lesson. So for today, the overview for today, we'll be having to treat topics like neutralization, precipitation. We'll also handle redox reaction and oxidation number, and also balance redox reaction. I know this is one topic that has been a bit confusing many a times. So we'll try to see how we can break it down today. Then we'll also be going into disproportionation reaction and displacement reaction. So these are the portions we'll be going into today. It might not really be that much of content for today. It might not be much content we'll be treating today, but that's all we have for this week. So let's head into the lesson straight away. So neutralization reaction. First off, we've all been hearing about acids and bases. We've been hearing about acids and bases, and many people, even before they entered senior secondary, they've been hearing about acids. But probably as you entered senior secondary, you started hearing about base, and you've been hearing stuff like titration, and I think titration is popular, quantitative and qualitative analysis, and we learned that, or probably we've not learned, but we should know that qualitative analysis is the same thing as titration, that is neutralization. Quantitative analysis is a different thing, but qualitative is the same thing as titration. So, and the reaction I undergo that happens during qualitative analysis is usually neutralization reaction. So what neutralization reaction is a reaction between acids and base, whereby you try to neutralize each effect. Acids and base are two extremes. Acids and base are two extremes. They are two pH extremes. If you remember when we had been taught about pH scale, they said pH scale is a scale that is numbered from number 1 to number 14. Then at the middle it is number 7. Then that middle is termed a neutral point, meaning any solution that you test with a pH meter and it gave a reading of 7, you can say that that solution is neutral, is neither an acid nor a base. And up until 5.5 till 8.5 is still around the range of neutrality. So 5.5 and 8.5, yeah, they are still around the range of neutrality. So when you see a solution that has a pH reading of 5.5 or 8.5, you can still tell that solution to be partially neutral. So when I remember saying that acids and base are two extremes, that is, they are the ends of a particular meter. If I say a straight, you have a rod, the extreme to your left and the extreme to your right, if you're holding it at the center, is how acidity and basicity, how they proceed. So as you move away from the center of a pH scale, as you move away from a center from a pH scale, you heading towards your left, that's heading towards 1. The solution that they are reading is reading that direction. They are becoming more acidic. While any solution that is becoming higher in pH value, maybe from 8, 9, 10, 11, 12, up until 14, they are becoming more basic. So now, acids and base, they are like light and fire. They are opposites, two extremes, like as I said. They are like light and fire. Both of them, if you bring them, so they're like water and fire. So when you try bringing them together, you bring something that is neither fire nor purely water. You get something that is in between, maybe a warm or very hot water. So it's neither fire nor is it water. So that's how neutralization happens. We have acids on one end reacting with base on the other end. Acid being very is it corrosive? I would call it. It's not really corrosive. Acid being very degraded. It has strong level of degrading properties. It can degrade almost anything, and base being highly corrosive. Bringing both of them together would get a, when you bring both of them together at a form of proportion or at a reasonable proportion, they become neither hot nor cold. They become something that is looking like a lukewarm system. That's something that is neither an acid nor a base. That's a point that you call a neutral point. So the reactions where you have acids reacting with base, any reaction where you have acids reacting with any base is called a neutralization reaction. And when neutralization occurs, when you bring an acid and you react it with a base, the product is many a times going to be a type of salt. It's going to be a salt and also in a solution of water. That's usually the result of all neutralization reaction, because when you try to neutralize, there is this kind of reaction between hydrogen and hydroxide portion of both the acids and the hydroxide and the bases. So when they react in a way, that will neutralize the acidic and basic properties, so that you then have a neutral solution if the reaction is allowed to proceed completely. So now the common acid neutralization reaction is the reaction between hydrochloric acid and sodium hydroxide. So these two acids are very strong acids. They are strong acids. Hydrochloric acid is one strong, very strong acid. The same with sodium hydroxide, NaOH. So we are seeing on the board here, we have HCl, that's for the hydrochloric acid, and NaOH, which is sodium hydroxide. So when they react, they give salt, common salt, NaCl, and water, H2O. So this is what a typical neutralization reaction happens to be like. Even if you are reacting another base with another acid, maybe the acid was H2SO4 and it was possibly reacting with maybe NaOH2, what would happen is it will still give you a salt and also water. It will definitely give you, every reaction between acid and base for neutralization would always give you one type of salt and water. Definitely, it always give you that. So whenever you hear the word neutralization reaction, your mind, or titration reaction, your mind, okay, not really titration reaction, because there are different types of titrations. When you hear the word neutralization reactions, you should know for sure that they are talking about reaction between an acid and a base to give you salt and water. Acid plus base to give you salt and water. Acid plus base to give you salt and water. So the salt may vary, the acid may vary, the base may vary, but it will definitely give you salt and water when you react acids and base. So the importance of this is it is used for titration in biological systems, and sometimes it is used, the knowledge of these neutralization reactions are used for balancing pH or examining the level of acidity or basicity of different samples, solutions, or materials. So before I leave neutralization reaction, I would like to explain what happens when, okay, not necessarily, because this is basic level. So what happens in a neutralization reaction is that hydrogen from the acid breaks off and pairs with hydroxide ion from the base. So when the hydrogen comes up as H, pairs up with hydroxide ion, which is coming out as OH. When OH blends with H, you'll be having HOH, and that is H2O. So that's why it always gives us water. then the other things that are remaining will then bond together to form the salts that we know. So that is why all neutralization reaction would always give you salt and water. So with that being said, before I move on to the next slide, I don't know if anyone has any question in regards this, so that I would be able to move forward. Does anyone have any question in regards neutralization reactions?
No, sir. Yes, I have question.
Okay.
My question
Okay.
is,
Let's make our question
that is used
snappy.
in antacid actions and wastewater treatment. Is it the salt or the neutralization reaction?
The neutralization reaction is what is used for this.
All right, thank you.
Yeah. So wastewater, why it is used in wastewater treatment? Because some wastewater, they could be acidic, while some could be corrosive, depending on the company or the industry that probably is releasing that waste or sewage. So when they are acidic, you will test this wastewater that is being released, and you test it for acidity, probably using a pH meter or one of the measures for testing acidity. Once you find out, then you can then know, okay, what would I need? Is it an acid or a base? Because the solution could be acidic, it could be basic. So once you found out, okay, from a pH meter, you found out, okay, this solution is acidic, you know you'll be needing a base to neutralize it so that it will not become harmful to the environment. So that's how the knowledge of neutralization reaction is useful. So let's move on to the next slide. Next, we have what is called precipitation reaction. Precipitation reaction. So at the beginning, I remember saying something about qualitative analysis and quantitative analysis. Qualitative, quality is when you talk about titration. Qualitative analysis is when you talk about titration. When you talk about quantitative analysis, that's when you're trying to examine parameters that are, examine elements or compounds that are present in a particular unknown sample. So that's a quantitative analysis. So, and this one of in quantitative analysis, one of the types of examination that is being carried out is examination for precipitation. So, what is precipitation? Precipitation is the term that is used to explain when you mix two solutions containing soluble salts. Soluble salts. You mix two solutions containing soluble salts, or two solutions containing soluble salts. You mix them together. Then, as you mix them together, they react to form an insoluble salt. So, what do I mean? We had let's say, let me use an example, but this is not realistic. I'm just trying to bring something into reality. Let's assume we had sugar and salt. You dissolve sugar and salt inside water, inside two separate water containers. It will dissolve completely. Sugar will dissolve completely inside water if the water volume is not bad. Salt will also dissolve completely if the water is not bad. So now, for precipitation, how precipitation happens, when you dissolve sugar in water, it will still give you your clear solution. It will still clear. When you dissolve salt also inside the solution, inside water, it will still give you your clear solution. You might not know that something is inside. So now, what precipitation is when you then mix these two together, and you then start seeing that instead of them to just form two clear solutions, you start seeing a new appearance, either with a neutral, either with a white color, black color, blue color, whatsoever color, but you start seeing new things appearing into the solution. Maybe it becomes chalky. It becomes like as if you pour them together and the thing started looking like milk. You pour two clear solution and as you pour them together, it happens to now turn out like as if the solution now has a new color. That process is called precipitation reaction. Precipitation reaction. So that's what happens in precipitation reaction is you would have two solutions containing soluble salts. Then mixing them together, it then leads to the formation of an insoluble salt. So this is what precipitation is. So that insoluble salt that is formed, that looks like powder or particle or color or whatsoever form that we can then see. Those particles we can see are what are now called precipitates. Precipitates. So like what we have in this diagram here, though this diagram is not really, this image is not really giving the idea well. So what happens is you have a solution, two solutions, you pour them together, or you have a solution, pour another solution into it, and as you pour in that other solution inside, both of them are clear, but as you pour a new solution, before you know, you start seeing either white will start appearing, or something will just pop up that will be like a new appearance. So those new appearances are what are called precipitates. They are what are called precipitates. Part of this is what is seen during titration to some extent. No, not really titration, because titration you actually put an indicator. But some reactions where you'd have like the reaction between let me see, what reaction was that self? Don't worry, if I can remember one reaction, one popular reaction where you see precipitation, I'll remind us of it. So what happens, from what I can see, from what I wrote here, but if you react silver nitrate or nitrate, reacting silver nitrate with sodium chloride solution, both of them are in salt, both of them are salt. Silver nitrate, and that is AgNO3. It's a salt. NaCl is our common salt. You dissolve both of them in water, it will give you clear solutions, two clear solutions. But now, when you then pour these two clear solutions together, you would find out that this AgCl, you will find out that there will be a new, you start noticing white particle will be formed, white coloration will be formed. So those extra coloration that is being added to the clear solution, the initially clear solutions, are what are known as precipitates. Those colorations are what are known as precipitates. So they could be white, they could be black, they could be blue, they could be any color, but so long as they are altering the transparency of the normal solution, they are known as precipitates. So there are different types of precipitates. There are gelatinous precipitates, there are powdery precipitates, there are different types. There are different types of precipitates. So long as they are colors or an appearance that appears in a previously clear solution, they are known as a result of after the addition of another solution. Any appearance that comes up is called a precipitate. I don't know whether that's clear. Does everyone get this drift? Does everyone get it? Okay, thank you. So now,
yes,
when they're writing the reaction of precipitation reaction, they usually use they mostly use an arrow indicating the precipitate, or the one that is a precipitate. So from this diagram now, you see here we had AgNO3 plus NaCl to give us AgCl, then a down arrow plus NaNO3, sodium nitrate. So what this downward arrow is indicating is that this AgCl was the precipitate that you would see on that reaction. Meaning that if you see a white substance, usually white substance, this is Ag. If you see a white substance appearing, that white substance is not sodium nitrate, it is AgCl. That's what this thing is trying to tell you. This arrow pointing downward is showing. So some other times you might see arrow pointing upward. When you see an arrow pointing upward, it's usually trying to talk about gases that are being evolved. But when you see arrows pointing downward, it's usually talking about precipitates that are being formed in the solution. So now, it is, from what I have it says it is used for qualitative analysis. Oh, sorry, I was making a mistake earlier. I was saying quantitative. I don't know that I was saying quantitative for titration and qualitative for this. Qualitative is the one that you use, what they call it. It's the one you use powder. They will be looking for precipitates, whether something was evolved, and you'll be drawing out inference. That's qualitative. Quality is that one. You're trying to determine what and what were present, the quality of things that were present in a particular unknown sample. So quantitative now is the reverse of it, where you're trying to check an amount of acid. That's what titration is. Quantitative is titration. We are trying to check the amount of acid that will be used to neutralize. So that's why I say quantity is for the acid. Acid and base is quantity. You're trying to check for the quantity of acid that will be used to neutralize. So it's a quantitative analysis. While qualitative analysis are the other ones where you'll be pouring different, maybe something like Felling solution, Meyer's reagent, all those things, all those kind of reactions where you're trying to check what sample A is, what sample B is, what sample C is. Those reactions are called qualitative. You're trying to check what is the quality of the unknown sample. So while quantitative is the one that is your normal titration volumetric analysis. So sorry about the initial mismatch. So I don't know. Everyone got what I have said so far?
Yes, sir.
Does anyone have any question? Probably
Yes,
Yes. So what you are saying in essence is that the precipitation reaction is used in quantitative analysis and not qualitative analysis as is stated.
No, precipitation reaction precipitation reaction is used for qualitative.
All right. So what you wrote is correct.
Quality is precipitation.
All
Yeah, what I
right.
wrote here is correct. It was an oversight.
Okay.
Yeah, thank you. So let's move on to the next slide. So now here is like I said, the meat of the lessons for today, because I think this is one of the topic that gets many people confused. But after now, I believe it should become simplified, so as many of us that will pay attention. So let's see redox reaction. The word redox actually was coined from the combination of reduction and oxidation. So when you hear the word redox reaction, they're just trying to tell you reduction and oxidation reaction. So that's where they coined the word out. So with that, I guess you probably might be having an hint about why it is actually about oxidation and reduction. So redox reaction are actually about reactions that are undergoing oxidation and also reduction. So first off, whenever you see an oxidation reaction, any reaction that you see an oxidation reaction happening in, I tell you this is an oxidation reaction, it means there is also reduction reaction happening at the same time. Both of them are activities that happen at the same time. Once there is an oxidation reaction that is happening, it means on somewhere else there is another reduction reaction happening for the reaction to actually proceed successfully. You cannot have oxidation reaction, only an oxidation reaction. You cannot have only a reduction reaction. So whenever you are saying maybe the main focus might be the oxidation or the main focus might be the reduction, that's why they will call it an oxidation reaction or a reduction reaction. But once you have an oxidation reaction happening, there is also a reduction reaction happening on the back view. So the reason for this is because oxidation, from definition of oxidation is the one that is a reaction that involves the loss of electron. Oxidation is a reaction that involves the loss of electron. So if a species is losing electron, it does not just throw away this electron. So since it's giving up electron, it means something is collecting the electron. So that's why I said reduction and oxidation reaction, they cannot happen on their own. They happen simultaneously. As reduction is happening, oxidation is also happening. As oxidation is happening, reduction is also happening. So oxidation is involving the loss of electron, while reduction is involving the gain of electron. Oxidation, loss, reduction, gain. So a simple acronym that probably would allow you remember this and not forget it is oil rig. Oil rig, where OIL is representing oxidation is loss, while RIG is meaning reduction is gain. So I think this is something that is similar to one portion of the Bible where they said, I will reduce so that he will increase, that kind of stuff. So, but the main idea here is oxidation is the loss of electron. The species that is undergoing, anytime they say the species is undergoing oxidation, it means it is losing an electron. It means it is losing an electron. So when they say a species is undergoing reduction, it means it is gaining an electron. It is gaining an electron, or is undergoing, it's gaining an electron. So now, this oil rig is an acronym that I see as being suitable for us not to confuse which of them is which. So oxidation is a reaction that involves the loss of electron, while reduction is a reaction that undergoes the gain of electron. So there is now this tricky part that probably most of the times is usually overlooked, but I think I paid attention to it at some point, and I feel this is very crucial. So we have that oxidation is involving the loss of electron. However, oxidizing agents are agents that gain electron, that collect electron. They are the ones that collect electron. Oxidizing agents, they collect electrons. Oxidation agents, they collect electrons. While reducing agents, reducing agents, they lose electron. So it's like the opposite. There is oxidation and reduction. Then there is oxidizing agent and reducing agent. So what oxidation is? Oxidizing agents, they are the opposites. What reduction is? Reducing agent are the agents that do the opposite. So if we said oxidation is the loss of electron, it means oxidizing agents are species that gain electron. If we say reduction is the gain of electron, it means reducing agents are the species that lose electron. So if you're writing down, just write it on one portion of your notes, because this is one part that is, I think it's easy to mistake. It's easy to mistake. Oxidation is the gain of electron, is the loss of electron, sorry, while reduction is the gain of electron. However, oxidizing agents are agents or species in the reaction that gain electron, while reducing agents are species in the reaction that lose electron. You get? So that is why you've heard this statement. It said oxidizing agents are reduced, while reducing agents are being oxidized. So in this sense that oxidizing agents, we say they gain electrons. So reduction is the gain of electrons. So they are being reduced, while reducing agents is they are being oxidized because they lose electron, from what I just explained now. So I don't know, it's a bit tricky, it's a bit confusing, it's a bit over your head, but just take it down. Oxidation is the loss of electron, while reduction is the gain of electron. Oxidizing agents are the species in the reaction that gain electron, while reducing agents are the species in the reaction that lose electron. So that's one thing I think that it's important that you take note of. So now, with that being said, let's move on to the next slide. Does anyone have a question before I move on? Probably for clarification. Okay, I will assume no. So let's move on to the next slide. So now let's go to when you hear I said redox reaction is talking about the general thing that happens in every reaction, reduction and oxidation. So redox reaction is a reaction that species undergo both oxidation and reduction. So now we have one portion in chemistry that talks about the balancing of redox reactions. So now I listed out some steps that I believe should be easy, that should make it easier to balance redox reactions. So I had this page titled steps for balancing redox reaction. I said in acidic solution, but not necessarily just in an acidic solution, but in acidic and basic solution. So I'll show you the portion that is for basic, or where they deviate, where acidic solution deviates from basic solution. So here we have the first step. You would split the reaction into two halves. You split the reaction into two halves. That's the oxidizing half and the reducing half. So when we get to the example, it will become clear. So the next step is to balance all elements of each reaction except hydrogen and oxygen. So the next thing is to balance all elements that are present in the reaction halves, leaving only hydrogen and oxygen. And we have the first step. I said the first step is you would have to split the reactions. Sorry, you have to split the reactions into two equal halves. So this is splitting the reaction into two equal halves. That's the oxidation half and reduction half. We will see how we can do that. The next is balancing all elements in each half reaction. That's except hydrogen and oxygen. So for this second half is very important. You balance every reaction. So when we get to the example, I think all these things we are listing out here would make more sense. So the next step after that is balancing oxygen by adding water, balancing hydrogen by adding H plus for acidic medium or OH minus for basic medium. So the next one after that is balancing the charge by adding electrons. The next thing is making the number of electrons equal in both half reactions by multiplying. So we'll see what these things mean. Then after that side, we will then add both reaction, then simplify if needed. So now let's move on to an example. So we'll see how these things apply. So we'll be coming back to these steps and moving forward so that we can be able to see how each of the steps apply. So this is the reaction. Now we have balance this redox reaction. And this is the redox reaction. We have MnO4 plus Fe2 plus to give us Mn2 plus Fe3 plus. So I said the first step you will do is you will split it into two halves. So these are the two steps. This is the first step. Split into two halves. So now, what this splitting into two halves means is you check the metals that are present. You check the metals that are present. Then once you found the metals that are present, you would write the red metal on the left-hand side equal to the metal on the right-hand side. That particular metal, where it is appearing on the left-hand side, you make it equal to where it's appearing on the right-hand side. Where it's appearing on the left-hand side, you make it equal to where it's appearing on the right-hand side. I think here we have Mn. This is the first metal we are seeing, Mn. So we will write everywhere we see Mn in this reaction on this left-hand side, we write it down. So that what we have here is only here, this MnO4 minus. Then Mn has finished on this left-hand side. So you now look at the right-hand side and check all the places you saw Mn on this side. It's only this place. So you now write what is there, Mn2 plus. You write it there, Mn2 plus. So we are done with Mn. So the next, you go to the next metal now. We have Fe2 plus. So Fe2 plus now, you write it down, Fe2 plus on the left-hand side. On the right-hand side, you have Fe3 plus. You write the Fe3 plus also. So we do it by splitting it like that. You've done the first step, splitting it into half cells. So someone wants to say something? So we've carried out the first step, which is the splitting. The first step is splitting the reactions into two equal halves. And to split it, you will check a particular metal. Everywhere it appears on one side, you write it out on that side. As Mn appeared here, appeared in another place, you write all the Mn appearance on the left-hand side of this place. Then all the places that Mn appeared here on the right-hand side, you write it also on this side. So fortunately for us, we have it just appearing once here and appearing once here. So we write it once here and also Fe appears once here and once here. So you write it also the same way, once here and once here. So now, with this now, the next thing they said, the second step, say balance all atoms except hydrogen and oxygen. So what they mean by balance all atoms except hydrogen and oxygen is you will check the number of Mn or any atom, any element that is not oxygen or hydrogen on the left-hand side. You check on this other right-hand side and see whether they are equal in number. So now, looking at this one now, we have, how many Mn do we have here? We have just one Mn on this side. How many Mn do we have here? Just one Mn. Ignoring the charge that is up. The charge is not the number of atoms. The charge is the oxidation number. But now we're talking is the oxidation number. So now we're talking about the charge. We're talking about the atom, just the number of atoms that are present. So we have just Mn1 here, Mn1 here. We have Fe1 here, and we have Fe1 here. So since both of them are equal, this other one is O. Oh, they say we should not balance O yet. We don't have H. As mean we had H, they would have not balanced H also, because we need to not balance O and H. It's only every other thing that are not O and H that will balance up. So other things that are not O and H, we have Mn, they are equal numbers. Fe, they are equal numbers. So that's what we have here. I said Mn is already balanced. Fe is already balanced. So the next step now. Yeah.
I have a question. Don't be angry.
Yeah, I can hear you.
What if the N at the right side is more than one? Like,
what if the Mn was more than one?
Yeah. Like maybe like the Mn at the right hand side was taller than the one at the left hand side. Like, what are you meant to do?
You would put let's assume now we had, let me say the scenario was now we had Mn, maybe 2 Mn on this side, then we have 1 Mn on this other side. You would put 2 at the back of the Mn on the other side, so that it will become balanced. So you might have maybe here, at this, maybe you might have Mn2, while on this side you just have Mn. So meaning that on this side we have 2 Mn, while on this other side we have just Mn. So since there are 2 on the left-hand side and 1 on the right-hand side, you have to balance it by adding it so that it will become balanced. So to balance that one, you put 2 at the back of the Mn on the other side. I don't know whether you understand what I mean by that.
Okay. You put 2 Mn. You put 2 Mn?
Yes, 2
okay,
Mn.
Sir. Okay. Or maybe 3 Mn, 4 Mn, that kind of stuff.
Yeah, depending on how many is on the other side. Your aim will be trying to see how you can balance both sides to be equal.
Yeah. Okay, no problem.
So even if you need, if you need you to put, if you need you to put 5, if you need you to put 6, you just do it like that until it
What
becomes
if they have
equal on both
different
sides.
charts? What if they have different charts? Like maybe
Leave,
like this one has MN minus, some MN plus. What will
leave
you
their charges
like?
first.
Would you say
Leave
ignore
their
it?
charges. Leave their charges first. Yeah, ignore the
Okay.
charges first.
Okay,
Yeah,
sir. Thank you.
yeah. So now
So
we
I have a
balance the
question.
atoms present now. Yeah, I'm listening.
The slide before this one, I
Yeah,
didn't understand. Yeah, this slide before this one.
that's this one.
No. Okay, is the one you removed now? Let me ask you a question there.
Okay, this one, yeah.
This one, yes. Here, uh, magnesium, uh, magnesium, magnesium
No
four
magnesium.
oxide. Is it 4 6?
Is
Eh?
manganese.
Manganese. Is it 6?
Manganese. N is
Eh?
manganese. Mg is magnesium.
Okay,
Mn is
manganese
manganese.
oxide. Yes, or rather manganese ion reacted with uh, iron to give
Yes,
manganese and then iron. Here you
iron.
said we
Yes,
could split into two half.
yes.
Splitting into two half, is it writing manganese oxide plus iron oxide? Then we now
No,
write
no. Okay, this splitting into two halves, what it is just like as if you have, let's assume we had um, boys on the left side, boys and girls on the left side, boys and girls on the right side. If you want to split the class into two halves, let's say we had the class had like two rows, two seats, two arrays of seats where you have boys and girls mixed on the left hand side, boys and girls mixed on the right hand side. So if you don't want to mix the right hand side girls with the left hand side boys, with the left hand side girls, you will tell the right hand side girls, oh yeah, all of you that are right hand that are on this right hand row, all of you should come forward. They will stay and stand in front of their line. They will tell all the girls on the left hand side, all of you that are here, stand and come to the front.
that we collect the like terms now together.
Yes, you bring all the ones that are belonging to one side. Like all the Mn now, we brought all the Mn, all these reacting agents that have Mn, we put them on one side. The reacting agent that have Mn on the other side, we also write it on the other side. Then you now come again, Mn has finished. You go to F, all the reacting agent that have F on this side, you write it down. All the reacting agent that have F on the other side, you write it down on the other side. So you splitted them into two equal halves. Into two halves, not
Okay.
even equal. It does not need to be equal, but yeah, into two halves. So then now to make
Okay.
the halves now equal, you will then start trying to balance off. So the next balancing step now is to check how many Mn was on the right hand side. 1. How many
I've not
Mn was on the
finished
right
with
hand
the
side?
splitting yet. I've not finished with the
You said?
splitting yet. I said I have not finished my question on the splitting yet.
Okay,
Now
okay,
I've understood
okay.
how the thing is splitted. And second
Yeah.
question is arrow. What does it indicate? Because I thought it will be manganese oxide plus manganese
No,
oxide
not plus.
ion plus manganese ion. So what's the
No,
role
we,
of
we are
that?
not we are not joining. The arrow
That
is like a
arrow?
demarcation so that the ones on the right hand, the arrow is like a demarcation such that the ones on the right hand side will not mix with the one on the left hand side. It's a demarcation because we are not trying to mix them together. We are not trying to gather them together. It's just like as if we had let's assume in some kind of churches, there's this kind of church where you'd have they will say men and women should not sit down together. Some churches. Then in those kind of church, maybe there was a mix up. Men on one row sat together with women on that row. Women on the other row sat together with men on the other row. So the first thing that they want to do, if they want to separate everybody, they'll say all the women on this row come out, you come out. All the women on the second row come out, they will come out. So that's splitting. You're not mixing them yet together first. You just first bring all of them out so that you now have women on the right, women on the left against men on the right, men on the left. That's what you're trying to do. MN on the right against MN on the left. FE on the right against FE on the left. That's what you're doing here. You're not trying to mix them. You're just trying to separate them into right and left, but only FE with FE. MN with MN. I don't know whether it's clear now.
Partially. So the arrow is just demarcating them.
Yes, it's demarcating them. They're not supposed to mix. It's just showing that, okay, this one belongs to the right, this one belongs to the left, but both of them are MN, MN. So it's just to bring them like, okay, we are both families, but now we are not supposed to mix. We're not together. We're not in the same place. Yes, they are the same thing, but they are not on the same side of the reaction. One of them is on the reactant side. The other one is on the product side.
Product side. Okay.
Yes.
Okay, thank
So
you.
then the next step now is balance. The next step now is balancing, checking for the number of MN on the left-hand side and also checking for the number of MN on the right-hand side. So we see here that we just have MN1 here on the left-hand side and we have MN1 on the right-hand side. So because they are equal, that's the MN half is balanced. So now you go to the FE. The FE on the right-hand side is 1. The FE on the left-hand side is 1. So because they are equal also, that one is also balanced. Take notes. The power up is not telling you the amount of that atom. The power up is not telling you the amount of the atom that is present. It's only if you see something like a small number down that will tell you that it is increasing, that number is more. Assuming we saw MN2O4, it means that there are 2 MN. Assuming we saw MN2O4, it means that there are 2 MN. But if you see MN raised to power 204, it does not mean there are 2 MN because raised to power is not telling you the amount that is there, it's just telling you the charge. But the one that is down is telling you the amount. So take very important note. Just that one is very important. I should take note of it. So we have O4, meaning that we have 4 oxygen, but we're not treating oxygen yet. O4 is 4 oxygen. Fe2 plus is not telling you that there are 2 Fe. It's just telling you that there's 1 Fe that has charge 2. On the second side, we have Fe3 plus. It means we have 1 Fe that has charge 3. So they are not telling you that there are 3 Fe on this side and 2 Fe on the other side. It's only if the number is at the tail, or that is at the bottom, or at the back, that it is the main number. So if the number is, let's assume it is 2 Fe2 plus, it means that there are 2 Fe. If it is Fe2 plus, it means that there are 2 Fe at the same time. But now, if the 2 is up, the ones up, you don't count those ones up as the number of atoms. They are the charges, not the number of atoms. So just take important notes.
All right, thank you.
So can we move on?
Yes, sir.
Yeah, let's move on to the next one. So the third step now is to balance oxygen by adding H2O. So you balance oxygen by adding H2O. So we'll check this reaction. Which of them has oxygen? It's only this one that has oxygen. So meaning that it's only this one we are balancing oxygen on. And we have, on this one, we have 4 oxygens. 4 oxygen. So now, if we are to balance it with H2O, what we are trying to balance, we're trying to balance the O to be equal. So since the oxygen is on the left-hand side, the place you balance it is on the right-hand side. If the oxygen was on the right-hand side, the place you balance it will be on the left-hand side. But now we have oxygen on the left-hand side, so we are balancing it on the right-hand side. Because we have 4 oxygen on this side, we don't have any oxygen on this side. It's supposed to be equal. If 4 oxygen is on the left-hand side, 4 oxygen should be on the right-hand side. So now we are balancing with H2O. So now to know the amount of H2O we are putting now, to know that it is 4 H2O, is because there are 4 oxygen. There are 4 oxygen. So when you put in H2O here, you have already introduced 4O to the right-hand side, which balances off with 4O on the right-hand side. So we have 4O on the left-hand side, balancing off with 4O on the right-hand side. Do you get? So to balance for oxygen, you would add water for this kind of reaction. To balance for oxygen, you add O. While to balance for hydrogen, you will see what. To balance for oxygen, you add water. You not just add O, you add water. So now we balance the oxygen here. Now the fourth step now is balancing hydrogen. So to balance for hydrogen, you add H plus. So now because we introduced hydrogen on this end here, so this is now the new reaction now of the Mn own side. The Mn own side is like this is the Mn own side reaction. It's no more the former one. The former Mn reaction was this. We had two half cell equations. These were the two half cell equations. But now we have upgraded this reaction to this one that we have on this page here. So while the former one is still remaining the way, the former Fe reaction is still remaining the way it is because nothing is balanced in here. So it's the same thing. So the Fe did not change, but the Mn changed. So now to balance for the H now, this one has H, this side has H, and this side did not have H. So now, how many H do we have on this side? We have 4 times 2. 4 times 2, because 4H2 is saying 4 times 2 hydrogen is on the left, on the right hand side. So we have 8 hydrogen on this side. So because we have 8 hydrogen on this side, we have to add 8H plus on this other side. That's why we added 8H plus here. So you just add it to this side, 8H plus on this end. 8H plus on this end. So that this is now be the new equation for Mn side. So we've upgraded the Mn equation now 2 times. So now this is the Mn equation, while the Fe equation is still remaining the way it is, does not change. It's still remaining like this. So we still have 2 half cells equation, but one of the half cells has been upgrading since we've been moving forward. So we are done with step 4. Is anybody confused at this point?
No, sir.
So now we tried balance. We had this equation from the beginning, and this equation from the beginning. So now we balance all the atoms, Mn and Fe. Mn and Fe, they are 1 1 on both sides. So we are good to go with those atoms. So now the next thing to balance now is the oxygen ends and the hydrogen ends. So first, the one we can spot out is oxygen end. So we will be balancing the oxygen end first. So to balance the oxygen end, you add H2O. So that's what we did here. We had MnO4 plus Mn2 plus. That was there. This one was not there before. This one was not there before. So just this one and this one. So now to balance the O on this side here, you would have to add, that is the standard rule, that whenever you are trying to balance the oxygen on one side of the half cell, you would add water to the other side of the half cell. So now on this side we have oxygen, but we don't have oxygen on this side. So to add oxygen to this side, we have to add water, because water has oxygen on it. We have H2, we balance oxygen on this side. We have 4 oxygen here and 4 oxygen here. So now to balance for hydrogen now, we add H plus. Whenever you're trying to balance for hydrogen, you add H plus. So adding H plus here now, we'll be doing it as this. We have 4 times 2 hydrogen. 4 times 2 hydrogen on this end is giving us 8 hydrogen. So meaning that since there is 8 hydrogen on this end, you have to add 8H plus. That's 8 hydrogen on this other end. So that's why we added 8H plus on this end. So having done that now, we've balanced for oxygen, hydrogen. We've also balanced for all the elements. So now the next thing to do now is to balance for the electrons now. That's the next step now. To balance for the electrons that are present. To balance for the electrons that are present. So now,
excuse sir.
we will look at this.
So
now.
that same side, that same reactant side, we have oxygen. Then we now balance the product side. So the same that same equation is where we balance the hydrogen.
Yes. From that same equation. Every time you update any equation, that equation will be the new. That updated form is what you'll be working with going on. You will not go back to the beginning. No. If you upgrade an equation, that equation will be the new equation state. So any other change that will be done on that new state. So don't go back to the beginning again.
Okay.
Yeah. So now the next thing now is to balance charge by adding electrons. So now how do we balance this charge now? On this end now, we have 8H plus. The charge of hydrogen is always +1. It's always +1. While the charge of oxygen is always -2. The charge of oxygen is always -2. And the charge on this MnO4, the overall charge, I don't know whether you guys are used to balancing of redox equation or balancing of or finding out oxidation number. To get oxidation number for any species at all, any group of atom, if that group has a charge on the top, that charge will be what it will be equal to. Like this one now, we have MnO4 raised power minus. It means that the whole of MnO4 are equal to -1. That's for MnO4. So while on this end now, we have 8H plus. H is positively charged. So we can say 8H times 1. 8 times 8 times plus 1, it will give us 8. It give us 8. On this side, we don't know manganese, its charge usually change. Its charge usually change. Oxygen is stable. It has stable charge of -2. So -2 times 4 is going to give you -8. -8 is equal to -1. -8 is going to be equal to -1. So when you do -8 minus 1.
Where did you get the -1?
The charge up, that minus that is up there.
Pardon?
The minus that is up.
On that
the minus
oxygen.
that is up. Yes, for
That
the
is
oxygen.
up at the MnO. That minus there, ma.
Yes, MnO minus, yes.
Okay, but I thought you said this -2.
No, I said oxygen is -2. Oxygen, generally, the oxidation number of oxygen is -2.
Yes.
So now, the MnO4, all of them together is
one electron. That's why it has -1.
It gained one electron, yes. Yes.
Okay, right on.
So now we have on this end now, O is -2 times 4, that is -8. Equal to -8 plus Mn. We don't know what Mn is. Equal to -1. I don't know. I wish I was using my system now. I would have been able to type it so people will see what I mean by this thing I'm trying to explain. Because now using my mouth, I don't know whether people would understand it very well, Sha. I don't know.
Just try to explain it. You understand.
Okay. So let's see. We have 8 oxygen here. 8 -8 on this side. This one has 7. -8 minus 1 is going to give us 7. So we know that the charge of this one is 7. So now, but the simple thing to do is you just take the charge. We know the charge of this one now. The charge of this entire species is -1, right? This entire species here, the charge is -1 up here. We are seeing this -1 here.
Yes.
So this -1 that is up here is what they put in as this -1 here. So now this 8, this hydrogen now, assuming this 8 was not behind this hydrogen here, we'll just have H plus. So the charge on hydrogen will be +1. Yes. So now because of the 8 at the back of the charge of hydrogen now, it's now be 8 times +1. You have your 8 plus here. Then there is no number behind all this one. So meaning that -1 is what you have as the charge here. So now this 8 now, -1 is what will give us 7 as the total charge that has happened on this left-hand side.
Okay,
Hello?
okay, sir, right on. Hello, we can hear you. Continue,
So,
right on.
We had this charge. This hydrogen has charge of +1. MnO4 together have a charge of -1. Both of them, they have charge of -1. So because they have charge of -1 now, you put their general charge as -1. Oxygen, that's the general charge of +1. So because of the number of 8 at the back, of oxygen. That 8 will now multiply the charge of oxygen. As mean we have something like 2 bracket open, MnO4 bracket close minus. That 2 will multiply this minus, making it minus 2. But because we don't have that 2 at the back of this place here, it's just going to be minus 1, the charge up here. That will be the charge for this entity. Minus 1. So the charge for hydrogen on this end is plus 1. So plus times 8 is going to give you 8 plus. Minus 1 is going to be here. So 8 minus 1 will give us plus 7 for the right hand side. So while on this, for the left hand side, sorry, while on this other end now we have Mn2 plus. On the right hand side we have Mn2 plus. So it's only Mn2 plus that's on that side. Normally if you see it here, we have Mn2 plus and hydrogen. Hydrogen does not have any charge. This water, water does not have any charge here. So because, okay, let's use here. This is the last modification we had. Water does not have any charge here. So since water did not have any charge here, it's only this one that has charge. So the total charge on this end will be plus 2. That is plus 2 plus 0. There is no charge here. So we assume that the charge of this one is 0, is neutral. So it's 0. So this one has charge here of plus 1 times 8 at the back. That is 8. This one has charge of minus 1. 8 minus 1 is giving us 7. So 7 is on this end. 7 and 2. 7
Sir,
and 2.
please wait, don't be wait. Please, I want to ask one question.
Yeah.
How do we get that plus 2? That plus 2 is it the charge that was on top of the Mn? That's the plus 2.
Yes, it's the charge. Yes, it's the charge that was on Mn.
Okay.
So let's look back at this step 4 now. This was the last state of this place here. This was the last state on this end here. Right?
Yes.
Yes,
The
sir.
last state of this Mn, their group, their last state was here. So now you check it. You start checking each of the entities. H has a charge of plus 1, but there are 8 of it. So 8 times that plus 1 will give you 8 down here. As I was in my pen, I would write 8 here. MnO4 together, they have a charge of minus 1.
Yeah.
They don't have any number behind them. So the answer for this place will be minus 1. So that's for this left-hand side. So 8 minus 1 will give you 7 for the whole of this left-hand side. 7 will be the charge of this left-hand side. So why on this other right-hand side now, we have these 2 on the right-hand side. The only one that has charge here is this one, Mn2 plus. This one does not have charge. Water does not have charge. It is neutral. So meaning that its charge is 0. So 2 plus 0 is giving us 2 on this end. So we have 7 on this end and 2 on this end. So that's what we had here as 7 on this end, 2 on this end. Right hand, left hand, right hand. Is it clear?
Yes, sir.
Yes, sir.
It's
Very clear.
not clear. From where did you get 5
Yes.
electrons?
5. We've not
Yes.
gotten there now. We've not gotten there. We've not gotten here. We've not gotten here. So we are still at this point here.
Step
I'm just
4.
trying to-
Step 4.
Step 4. See step 4 here. So on the left-hand side of step 5,
I
we have
question on
7.
Step 4.
Yeah, I'm listening.
In that step 4, the right hand side should be plus 2 plus 0 because water is 0,
Yes.
it has no charge. So it has
Yes.
to be plus 2. Then on the left hand side, the hydrogen there is 1 times 8 hydrogen, which is
Yes.
8 electron, which is 8H.
That's 8. That's 8 here. 8 first. Then MnO4, we have minus 1. MnO4 had minus 1.
Okay.
So that minus 1, it does not have any number, any coefficient at the back. So it's just going to stay as minus 1.
So how do we reconcile it with the 8H?
So you now do 8 minus 1. It will then give you 7. So that we had here. This is the 8H here. This is the 8 here. And this is the minus 1 here. So 8 minus 1 will give us 7 for your left-hand side.
Okay.
So then this is the right-hand side now. Right-hand side is only Mn that has charge. That's why it is only 2 plus for the right-hand side.
Okay.
So now, to balance, we've just gotten the oxidation, the charges, the total charge on both sides, left and right-hand side for Mn. So now, to check the electron, to balance the electron now on both sides, you look for the one that has the smallest charge. Right-hand side or left-hand side, the one that has the smallest. So this one has the smallest, 2. Left-hand side has 7. 7 is bigger than 2. So now, how many would you add to 2 that would make it up to 7? 5. So because it is 5, that is the number of electrons you add to 7. Because your aim is to try to reduce the number of electrons. So it's like as if you're trying to tell you that this one has 7 positive charges. This one has just 2 positive charges. So how many negative charges can you add to this one to make it become the same with this one? Electrons are always negative charge. So how many negative charge will you add to this one to make it equal to this one? Simplest way to explain it is look for the smallest one, the smallest side. How many is remaining to make it equal to the highest side? If you can find that in, just add that into the highest side and put as E. So that's why we have 5E on the side that has the highest. The left-hand side has 7, but yet we are still adding 5 to it. Because this 5 is not just normal 5.
Wait, you said that the left-hand side is 7.
Yes.
Plus 7.
Plus 7. Yes.
Right-hand side plus 2.
Yes.
We look for what?
You look for how many? The smallest between 7 and 2 is which one? Is 2, right?
Mm-hmm.
So now, how many will you add to 2 that would make 2 equal to 7? 5, right?
Mm-hmm.
So that 5 you get, you would now add it as the number of electrons you add to the right-hand side. That is biggest.
Okay.
So now you just like saying, to whom that has more, you give more electron to him.
Okay.
So you check between the left-hand side and right-hand side, which one has more electron? You check. The one that has more electron, is it left-hand or right-hand side? The one that has the lowest electron, you say, okay, you have the lowest electron. How many does it remain to add up to the highest, to get to the highest electron? They will tell you. Once you found it out, instead of it giving to the one that has less, you would follow the law that says, to him that has more, you will give more to that same thing. So that one that has the biggest, that's one that the extra that is supposed to add the smallest one to make it equal. You add it to the other one, but you add it as electron, not just as 5. You add it as electron, so that will now become 5 minus. So that 5 minus now, when you add 7 plus minus 5, when you add 7 minus 5 now, it will now be giving you 2 on the left-hand side, 2 on the right-hand side.
How?
The total we had on the left-hand side was 7, Shay. Here, we had 7. 7 plus, right?
Yes.
7 plus. So if you now add 5 minus on this side, what would happen?
Is it 5 minus or plus 5?
See, now, electrons always have minus charge. See, it's 5e. So this E is the charge of electron. Negative.
Okay.
So that 5 minus is what is making it minus 5. So 7 plus 7 minus 5 will then give us plus 2, making our left-hand side equal to our right-hand side. So that's the logic behind it. But now I'm not trying to simplify it in a way that you don't need to be thinking twice. Just check the one that has the lowest. Just note it. Then check that lowest. How many would it need to complete to the highest? Once he has known how many it needs to get to the highest, he put it as poison and give it to the highest. That poison, I mean, is just that negative, E negative is what you take it as. Because like as if the poor guy, he has just maybe 2 million. The rich man has 7 million. And the poor guy will be like, it remains 5 million for me to reach the same money with this rich man. No. Instead of me to add it to himself, he said, instead of me to add it to myself and to look somehow, instead, I want to make the other person way there high. main income, then I'll give him bad money, 5 million naira, bad money. When he will give him the 5 million naira bad money, he would now add it to the other side own. So when he adds it to that side, that bad money would deduct from the big side's own. This big side own will now reduce now to become small, because when you add negative to the big side own, it will drop in value. I don't know whether it's making sense.
Yes, yes.
So it's just like as if there are two business people. The one that is rich, he was doing his business. The one that is poor was doing his business, but he was not greedy. See, this big person, he has 7 million, me, I have 2 million. Instead of me to hustle to add more to his own side, he now said, instead of me to do that, I'll put juju that will be equal to the one that is supposed to make his own equal to my own. So the juju now that's supposed to make him grow by 5, he now puts that energy and put as juju negative, minus E, and add to the other one side, put on that one's domot. Then when he adds down the domot, now that one will now become down to his own level, because he will reduce to his own level. So that's what is happening in Nigerian. If I was put it in Nigerian explanation or Nigerian setting. So I don't know whether it's clear. Is everybody getting this thing?
Very clear.
Yes,
So
sir.
they are balanced because they have +2, +2.
Yes,
Right
both
hand
sides
side
are now
has
plus
+2.
2 plus
Left hand
2.
side has +2.
Yes. So now the same thing you did to the MN side, now you will now go to the FE side. Remember that the last FE side we had was this. This was the last FE side we had. FE has not changed since. It's just FE2 plus equal to FE3 plus, right?
Yes.
So the charge on this left-hand side is 2 plus, while the charge on the right-hand side is 3 plus. So now the same thing is happening now. The same market condition is happening now. The one that is poor, he has 2 million. The one that is rich has 3 million. Instead of the one that is poor, they have 3 million to now carry the riches and add to himself. He will not add it to himself. Instead, what he will now do is he will now look for what would make the other one become his own level. Look for one and add. As opposed to make him add, he will now put as juju and put into that other one side, so that now become, instead of his own to become +3, it now drop down to minus, it now become +2. So that's what happened here. We now added negative here to this side. That's negative. We did not put any number, just one negative will make this one equal. I don't know whether it's clear.
It will make the iron 2 equal.
Yes, to make the iron 2 now equal to the one on the iron 3. Instead of the iron 3 to be 3 million, instead of the iron 3 to have 3 million now, they have put juju, 1 million naira juju to his own end. And that 1 million now is this 1E, that's E raised power minus 1. E raised power
So
minus
it has
1.
lost 1 electron.
Yeah, it has gained 1 electron, because when it gains 1 electron, it drops. It's thinking that if they gave him a good thing, the electron that they added to it supposed to be an addition. But now that electron is a bad thing. So because it's a negative that's adding, it is now dropping its own value from 3 that it was before, that it was big. It's now dropping from 3 now down to 2. So that's how I use the juju explanation. This one had 2 million. The other one has 3 million. Then because of jealousy, he said, I'll go and meet Babalawo that will give me juju. How many is the Babalawo will now ask him, how many remain for your own, for your money to reach him money? He say, okay, I get 2 million, he get 3 million. How many remain? 1 million to complete. Okay. No, I'll take this 1 million. Go drop him for your own domot. Once you add that 1 million to the domot, it will become equal to with you. Anyhow. So that will just happen here. They now added the 1 million here, this 1E here. And when you add that 1E here, automatically both sides will become equal. I don't know whether it's clear.
That last equation, explain it more. The iron 3 lost electron.
Okay. See it like this now. See it here. We have 2 plus on this end, right?
Yes.
2 plus on this side, 3 plus on this side, Shay?
Yes.
So now, what will be added to 2 to make it equal to 3?
1.
So that 1 now, you add it to this side, to 3 side as electron.
Mm-hmm.
So now, such that you now be having 3 plus, that is 3 minus 1. It will now make it 2 here and 2 here.
So now, this is this gain of electron or loss of electron?
It was gaining electron.
So it gained.
It gained electron. This one added electron here. But the process going from here to here is loss of electron. Going from here to here is loss of electron. I'm not trying to, because if I should use the exact chemical terms, it will be confusing to almost everybody. I'm trying to bring it down to the level where
this place you added 1 electron. You added one electron to the ion 3.
Yes.
So my question there is that gain of electron or loss of electron?
Loss of electron. Fe, if you are going from left to right, Fe is losing an electron and becoming, because when you lose electron, it becomes more positively charged. So that was happening here. Fe2 plus is changing from Fe2 plus to Fe3 plus. So it means that it's losing electron. This is the electron that is losing here. It's still a bit confusing. The main thing I want
It
the main thing I
lost
want you to just get.
electron to be equal to Fe2.
It lost electron to become Fe3. This is the reason why I did not want to use loss of electron. The reason why I did not use loss of electron and gain of electron is because of this confusion. Because that concept alone, you need to actually have gotten to understand things like on a broader level for you to be able to get that sentence where the way it will be. This one now, when in the world of redox reaction, loss of electron leads to increase in number of charge. Every loss of electron leads to increase in number of charge. So Fe2 plus going from Fe2 plus to Fe3 plus, it is increasing, meaning that it actually lost electron to increase. Because for them to increase, they have to reduce or to lose electron for them to increase. So Fe at the beginning was Fe2 plus. Then when it lost electron, it became Fe3 plus. That's just what happened.
Okay, now I understood what you are trying to do. What you are trying to explain is this Fe2 that gave rise to the Fe3 by losing electron.
Yes.
Okay.
Yes.
It's clear now.
Yes.
But
So is
sorry,
everybody following?
Sir, please wait. Should the Fe2 plus still remains Fe2 plus and that the Fe3 plus still remains the same, but those are the added E minus to it
Yes.
to the
Yes.
equation.
Yes. Yes.
Okay, sir.
Everything remains the same. It's just the addition of electron that is happening because that's how you balance for number of electrons. So now, once you balance the electron on the left-hand side and you balance the electron on the right-hand side, the next thing you do is you go to step 6. You go to step 6. Then now you now balance electron on the first half with the electron on the other half. You then check it. So if you look at this, the electron on this half, the total electron on this half, on this half now. If you look at them here, grouping all the right-hand side together, the electron on this end here is 5, right? Hello?
Hello, sir,
Hello?
please.
Hello?
What did you say?
I said after you balance the electron on each half one by one, which we just did, we balance electron on this end, right?
Yes.
Yes.
So then next you now check, looking at all the right-hand side, just look at everything. All the places that you have 5, all the places that you have E minus on the right-hand side, add them together, all the E minus you have. All the E minus we have on this side is 5, right?
Sir, please, your next slide. I want to see it. Thank you, sir.
So now I'm trying to explain how we did this, how we got to this next slide. We balance the charges on each of the half equation. So the next thing now to do now is to balance the equation, the electron on both halves. So looking at this one now, we had on this end now, on this Fe side, we have just one electron here, one E on the left-hand side here, and no E on this side. Here we have 5E on this side and no E on this side. So the total E on this side now, on all the left-hand side is 5. While the total E on all the right-hand side is just 1. It's just 1. So because there is no balance on both sides, left hand and right hand side, you then check how many E is on this side that is making it deficient on the other side. Sorry. How many electrons are on this end that can make it equal to the electrons on this end? We have 5 electrons here. We have 5 electrons, but we have just 1 here. So now we cannot just add it like that. We cannot just add 4. Just say 4 electrons here. We have to use a multiple. So we have 5 on this side, 5 electrons on this, totally on this one. So the simplest way to do this thing now is you take the total number of electrons on this side, on this other equation now. Sorry about that. The total electron on this half, you multiply by the total electron on this half. That is the simplest way to balance it. You take the number of electrons here. The number of electrons here is 1. While the number of electrons here is 5 on this one. We have the highest electron here is 5. All the electron here is 5.
Sir, please.
All the electron here is just...
Sir, please.
Yeah, I'm listening.
So you do 5 times 1 now. That's 5E minus times E1. Sorry, E minus, sorry.
It's
multiply
not times,
everything on it.
Is it
No, you
addition
times so.
Huh?
No, you multiply. You multiply. You multiply the coefficient of E on this side by everything here. And the coefficient of E on this side by everything here.
Okay.
So the coefficient of E on this side is 5, right? You multiply it by everything here. So you now be having 5 times F, 5 times Fe2 plus, 5 times Fe3 plus, and 5 times E. You will now be having 5 Fe2 plus, 5 Fe3 plus, 5E. Then you now check the charge on this one is 1. The charge on the number on E is 1. So you multiply 1 here. 1 times 8, this is giving you the same thing. 1 times this, 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 the same thing. So that way you now have this here, this equation, and this one. Where is that thing? This equation and this equation. So they did not join it. They did not show it one by one. But this equation now, it has the same 5E.
Sir, please wait, don't be angry. So you use that 5. So use the electron, that is the 5E to times all the Fe, all the Fe's, like all the ions.
All everything on this end. So assuming we had 3 here, assuming we had 3E here, and we had 2E here. Listen, assuming we had 2E here and we had 3E here, what we would do is we will multiply 2. If 2 is here and 3 is up here, you will take the 3 and multiply everything down here. And you take the 2 and multiply everything up here.
So,
okay, sir.
So in that sense, the left-hand side, we have to multiply it by 1. Then the right-hand side, we multiply it by 5. Is that?
Not the right-hand side. Not the right-hand side, not the left-hand side. The FE side, you multiply by 5. The FE half, you multiply it by 5. While the MN half, you multiply it by 1. So this is the MN half.
That's what I'm saying.
And you were saying right-hand side. That's why I was saying it was not right-hand side. Because it's everything. You multiply the 1 by both right-hand side and left-hand side. The same thing. Multiply the 5 by both right-hand side and left-hand side.
Okay.
So that we'll be having, this one will be the final answer for this side. And this one will be the final answer for the other side. That way you balance out all the electrons.
So the MN side.
Yes. Everything was multiplied with 1.
Okay.
While the FE side, everything was multiplied with 5.
Hello, sir. Please, why do you still have 8
of the same ion? The multiplication is of the same ion.
Because we used 1 to multiply all of them. That's why we still have 8 and MNO minus 4.
Use 1. Like use 1. The 1 at the back of this E here to multiply everything. 1 times this is going to be the same thing. 1 times this is going to be the same thing. 1 times this is going to be the same thing. 1 times this is the same thing. 1 times this is the same thing. So now then you do the one that's at the back of this one is 5. So you use it and multiply everything here. So 5 times this is going to change this one to 5 FE. 5 times this is going to change this one to 5 FE. 5 times this is going to change this one to 5E. You get? So that's why we have 5 FE2 plus, 5 FE3 plus, and 5E here. Okay. See what is happening. See what is happening. First thing I said is you check all the electrons on this left-hand side. We have all the E that we see here. The main thing is you even check all the E on the left-hand side and all the E on the right-hand side. So we have 5. As mean there was yeah. Normally from the beginning I said that this is the meat of the whole lesson. This redox reaction, and that's the reason why I'm not minding going back and going forth, going back and going forth. So let's be patient. If we are patient, this now, we'll be able to get. So the idea, we've been able to get how to balance, how to split into half cells. That one is gone. That's the first step. The next step now after splitting half cells is balancing the elements. Once you balance out the element, next thing is balance the oxygen. Once you balance out the oxygen, next thing is balance the hydrogen. Once you balance out the hydrogen, the next thing is now to check the oxidation number, to check the charge, balance the charge of both sides by adding electron. Then do the same thing to the other end. Once you've done that, you now go to equalizing now the electron. Equalizing the electron. So this phase here is the place I think is getting people confused, this portion. So now the idea here, the idea is to make the whole electron on this end to be equal to the whole electron on the left-hand side to be equal to the whole electron on the right-hand side. That is the whole idea. That we are trying to do all this balancing 1 minus of everything here, 5 times everything here. That is the whole idea.
Hello, sir.
That's the whole idea here. Yeah, I can hear you.
From what you are showing us now, is the MN side now, that is the left-hand side. Whereas the ion is the
MN
right
side,
hand.
like I'm trying to tell you, don't confuse, don't say MN side, left-hand side. It's not left-hand side against right-hand side.
Okay.
The time you're doing minus right-hand side is when you check the electrons here, the total electrons here. We have 5 electrons on this side totally. As mean I had a pen, I would have written it out for you people, like written it out directly. You'll be having 8H, MnO4 minus, 5E minus, Fe2 plus. Then that's everything on this end. Then now on this other end, now we have Fe3 plus, Mn2 plus, 4H2O, E minus. We have only 5E on this left-hand side. All the left-hand side, only 5E is there. While all the right-hand side, only 1E is there. And that 1E was as a result of this guy. So now, because we need to balance the 1E, the E, we have to multiply the E by this one here, by this end. The easiest way to balance it is by multiplying this one by 5 and multiplying this one by 1. That way, when you multiply that way, you would find a way to get the balance completely. And the reason why this is working is because the E are on equal opposite sides. The E is on this side, on the left-hand side, on this side. The E is on the right-hand side of this side. I'm trying not just to bring it at the simple level first, because when you meet other examples, you will start seeing that there are variations, a little bit of variation, but the idea is still the same thing. You're trying to balance the electrons. So to balance the electron on the left-hand side, if you write everything out one by one, you'll be having 8H, MnO4, 5E, Fe. You have written all the left-hand side. Then to now balance all the right-hand side, you'll be having Mn2 plus, H2O, Fe3 plus, E minus. So now on the left-hand side, we have total of 5 electrons. While on the right-hand side, we have total of just 1 electron. So now, before you can do that before you join them together, you have to balance the electron first, such that it to be equal. And the easiest way to balance the electron is take the number, the charge, the coefficient of electron here. As long as on the left-hand side, you multiply it by everything here. Take the coefficient of electron on the other side. So long as on this right-hand side, multiply by everything here. I would have loved to bring another example where the scenario is different, so it would get clear. If this place here, I mean there was another electron on this end here, you would have added that electron with this electron to know the total electron on the left-hand side. And if there was another electron here, you would have added everything here. So that you cannot, the main thing is now to get a balance between the two E here and the E here. I don't know whether everybody's with me.
Yes.
Yes.
Bring the slide, the next slide, where you inputted it, so that we can. Uh-huh.
So now we multiply the E now by 5. The FE, sorry, by 5. And the MN, we did not multiply it by anything because the one we multiplied by is the same thing that will show us. So now, having done that now, the thing what you now be left with now is you have this as
Here now
FEM.
this is addition now and not multiplication in this step 6.
Where is addition?
It is multiplication, ma. You multiply it.
5 FE 3.
FE was not having 5 before, remember? So how did FE have 5? We multiplied 5 from MN side by the 5 on FE side. So that's how we got to this point. That's what this step is about. So that they said MN half has 5 electrons. So multiply FE half by 5. That's what we did. See what they're saying? MN side have 5 electrons. FE side does not have 5. It's just only 1. So you multiply this FE side by 5. As mean FE side had 3 here. What you would have done is you multiply FE side by 5, multiply MN side by 3. So that when you multiply this one by 3, it will be giving you 15 here. When you multiply this 3 that was here by 5, it will be giving you 15 here. So you will be having 15 electrons here, 15 electrons here, and they can be able to be equal electrons. The aim is to get equal electrons on both sides of the equation. So this, luckily for us, this equation was simple, that we just need to put in multiplication of minus to this FE end. For the sake of time, everybody, what would happen is I will try to get a simplified video. I will send it to the group tomorrow, like a simple video where I'll try to illustrate with writing, like not really hand pen writing, but it will be
us here.
You said?
From this equation now.
Yeah.
Just explain this this equation under step 6. That is what I needed to understand very well.
After you would have to first get these points now. Once you've gotten these points now, you can then go to step 6. Once you've gotten the 5E, once you've gotten 5E on this side, on the FE equation, and you have 5E also on this MN equation, once you can be able to get that balance, you can now move on to joining both of them together. Joining FE,
no, I'm not
this one, adding this
equation under this step
with this
6.
one.
Yes, that's what I want to understand. I do understand that equation. 5FE 2 plus.
You would add all the left-hand side together. You would join all the two halves together. Left-hand side with left-hand side. This left-hand side of M, let me go back here. See here, we have all this thing on the left-hand side of this side. Then we have all this thing on the right-hand side of this one. So you add them together so that you'll be having 8H plus MnO4 plus 5E plus 5Fe2 plus. So that's what we have on this side. But now they remove the 5E because the E on this side would cancel out the E on this other side. Let's see how it's cancelled out. So on the right-hand side of this one, we have Mn2 plus 4H2O plus 5Fe3 plus 5Fe minus. So we have minus, we have 5.
Where I have issue is this 5Fe2 plus. Then on the right hand side, 5Fe3 plus 5 electron. That's where I need explanation. I understood other ones.
This point here, Che?
Yes.
This point here was gotten from this point here, was gotten from this end here.
Okay. Okay, so you multiply everything here by 5.
By 5. Yes.
That's what I really needed to know.
That I've been saying since. That I've been saying since. That I said the MN side 5FE multiplied by the FE half. So the FE half is this. This is the FE half. We multiplied everything here by 5. And that's how we got this end here. So after you've gotten that, you now add both sides. You add both halves together. Left-hand side to left-hand side, right-hand side to right-hand side. Then once you've added it, you'll be having an equation that looks like this. But you have plus 5e, and you have an equation that looks like this, plus 5e on this side. So the 5e will cancel out 5e. So this will now be what is left. And this is the balanced redox equation.
I've understood this FE very well. So the MN side, I'll multiply by 1.
Yes.
Don't be annoyed. Bring that equation on MN where our electron was added. This side. Please, don't be annoyed.
Is everybody on the same page? Let me have any different opinion, right?
So what I have is I will multiply everything by -1 electron.
Yes.
Okay.
By -1, not -1 electron, by -1.
Okay, by -1.
And not even minus, by 1, not minus. Don't put minus, by 1, not minus, just by 1. And this other one by 5.
Okay. So, and my equation will remain the same now.
Yes, we remain the same.
Go to the next step.
So then that equation that remains the same, you add it to this equation that is here.